Okay, so hello everyone. Now today I will start to talk about the new chapter, which is extended surfaces. Okay. So extended surfaces, we mean fins. Famous name is the fins. Okay, so fins are everywhere. Yes, I will show some examples of the fins, applications of the fins, and the equation of the fins, and why do we need them. First, we should start. Why do we need fins? Okay, think that I have a surface here. This is called base. Okay. I have a surface here, and this surface is very hot. This is hot surface. The temperature can be, for example, 100 degrees Celsius or 200 degrees Celsius. We don't know the temperature. I want to cool the temperature of the base of this surface. This can be three-dimensional also. In this case, you are looking for one dimension. Okay. So to cool that surface, you will need convection. There is also radiation, but here we are dealing with the convection, and assuming that convection is more than the radiation, or it combines the effects of the radiation, it is convection coefficient, convective coefficient. Okay, if it is convection, you will have H, you will have AS, and you will have delta T. Delta T is temperature of the base minus temperature of the environment. So first thing here is that you can increase the value of H for better heat transfer. And we know that H is function of velocity, okay, most of the time. So if you increase the value of H, it means that you should use something that increases the value of the velocity of the medium. So here, let's say it is air. Okay, air has low H. So therefore, in other words, air doesn't want to accept heat. It has very low H. So to increase the amount of H, we should increase the velocity of the air. So to increase the velocity of the air, you should use some means, for example, fan. This is the one option, to increase the value of H. Okay. Another option is, we will leave this one to the last part because that is our topic. And then you can decrease the value of the T infinity, which is impossible because this is environment. We have some fixed amount of temperature. We cannot decrease it in most of the conditions. Therefore, it is impossible. Base temperature. It is also not possible to decrease base temperature because you have some materials that you have used and you cannot change all of the materials, all of the design process. Therefore, the base temperature, again, most of the time is not possible to change. For example, if it is electronic circuit, there are fixed materials that are used in electronic circuit. We will have some base temperature, therefore it is impossible to change the base temperature. It's also not good. You have one option that is left, which is surface area. To increase the surface area of the base. So again, to increase surface area of the base is not a good option because say that you have an electronic circuit like this one and you are making electronic circuit like this one. Most of the places are empty because you are increasing the surface for only increasing heat transfer. Therefore, this is also not good option to increase the base area. What we are doing here is that we are adding surfaces to that base. This is called extended surfaces. In other words, we are extending the surfaces. Okay. And this extended surface, if you have AS1, it adds one more AS, which is AS2. So you have more surface area, and then you have better heat transfer. Then this extended surface is called the fin, and it's also called the rib. Okay. These are the different names for one thing. So we could have different shapes, different forms of the fins, and with the different efficiencies. We will talk about it, but now let's talk about the applications of the fins. So fins are used in most of the machines. We can start with the car engine or motorcycle engine. Any engine, you have the fins because engines are hot. This base, you see the base, this one is hot, and to cool that hot base, we need the fins. You see the fins here, you have another fin here, you have another fin here, see the three-dimensional fins, three-dimensional fins, three-dimensional fins. Or you use fin in electronic circuit. For example, this one. We have a lot of fins here. And we have also fan here. Fan increases H and the fins increases AS, although we will have good heat transfer. And also in heating systems, we have the fins here. Okay, the fins here. There's also three-dimensional you have into the page. And also you have the car radiator. Okay. There are lots of fins here. Okay, so you can see one fin here. Go into that dimension, you have another fin. Okay, there are lots of these fins in car engine. Or you have, these are the CFD simulations. So you have here hot temperature. You can see the temperature here. It is very hot. It's 47 degrees Celsius here. The temperature is 47. Okay. By attaching fins, you are decreasing the temperature. You can see at the tip of the fin, you have a temperature of 29 degrees Celsius. Almost 20 degrees temperature drop. Here also the temperature is hot and you are dropping the temperature by using fins. To analyze fins, we are using approximations. These approximations are called the Mori Gardner assumptions or approximations. There are 10 of them, okay? But the famous ones are these 6 that we are using. The one is that we are saying that the fins are one-dimensional heat transfer objects. What do we mean by one dimension? So say that this is the base. Okay, we are assuming that heat leaves the base by conduction in only one direction, in this direction. Why the heat doesn't leave the base in transverse direction, for example, in that direction? Why it doesn't leave? Because the thickness here, you see that this thickness is very small. So thickness is very small. If it is very small, then we can say that the temperature here and at the back of the fin, they are almost the same. If it is the same, there cannot be heat transfer, but the heat changes along the fin. Therefore, you will have heat transfer from the base to the tip of the fin. Or here, you have the hot base, the heat transfer leaves in one direction only. You don't have heat transfer in transverse direction because the thickness of the fin is like a paper. It is very small and therefore you have no any heat transfer in other directions. Good. This is the one thing. Another one is the steady. Steady means that you don't have any heat generation. It is also included in the third option. You don't have any heat generation or depletion. In other words, it means that you have, show it, whatever, if you take a small volume here, let's say that this is the small volume that we have here, you have some heat transfer by conduction, QCD. You have heat transfer out of the volume by conduction, QCD. And you have also convection by the environmental air, okay, convection. The steady means whatever comes into that small elemental volume is equal to the leaving on that elemental volume. Whatever comes, that leaves. Okay? Therefore, it is steady. There are no any transient effects happening inside this control volume. And constant K means that the K value is independent of the direction. Say that you have a K value of 15. If you go that direction, it is also 15. If you go that direction, it's also 15. If you go that direction, it's also 15. Therefore, atomic structure of the material doesn't affect the value of the K. K is constant in all directions. In other words, it is isotropic material. And the H value of the air is uniform, so there is a room H that flows across these refrigerator fins. So you can see the fins here, so these are the fins. Okay. The tubes are hot, this is the base, and you have the fins on it. The tubes are hot, these tubes are hot. They are using fins. So the room air that flows across it has H value which is constant. Okay, here also you have the H value, here also you have the H value, here also you have the H value. Blows of it, okay, so that's constant H. And we will deal with this one in next slides, okay. So we should have the optimal number of fins. If there are lots of fins, say that you have one fin here, another fin very close to that one, another fin very close to that one. So this one is not good. Why it is not good? Because now air cannot enter in between the fins. Okay, if air cannot enter in between the fins, then the convection heat transfer will drop. If convection heat transfer drops, then the adding fins doesn't bring any advantage. Okay, it is very similar to if you have a line and the clothes on it, you have clothes on that line. Okay. If these clothes are very close to each other and this distance is very small, then it means that air cannot enter between the clothes and this one will be always wet. So you have another line here, you have another line here. Therefore, air cannot enter in between the clothes, and therefore the clothes will be always wet. Good. These are the main approximations, and this is the main part that we should consider. Okay, we have different types of the fins according to geometry. We have the angular or radial fins. This one means that we have a cylindrical object. This one is cylinder, and we are attaching that cylinder object in radial direction, the fins. Okay, you have two fins here, can be 10, 15. And we have straight fins. Straight fins means that they are attached to plane. You have the plane, you have the fins attached to it, and these are called the straight fins. So this is also plane. So pin fins or spines are circular form. These are circular form. This is also circular form. Yeah. These are circular form pins. And another thing we should consider is that the uniform or non-uniform. If the fin cross-sectional area doesn't change as you move along the heat direction, this is the direction of Q dot Ct. We move along the direction of Q dot Ct. If this cross-sectional area doesn't change, it is uniform. If the cross-sectional area changes, it is non-uniform. So why do we need uniform and non-uniform? You will see that for uniform areas, we have the analytical solutions that we can use by pencil and the paper. But for non-uniform areas, we have the ready formulas that we applied. Okay, here the formulas are ready. And the difficult, this one we can say difficult. And this one are the easy, and we are most of the time dealing with these uniform areas. If the area is non-uniform, we will use either charts or the table. Okay, but this one we will use formula itself. Similar here. So if it is uniform, you use the formula itself. If it is non-uniform, we are using chart or the table. Okay. Good. Now this is the fin equation. We will not derive the equation for the fins, but we can give the concept how it is derived. We are taking a small elemental volume in the fin. This one is a small elemental volume here, small elemental volume here. And for that small elemental volume, you are applying the conservation of the energy. So conservation of energy says that if it is steady and one-dimensional, you have one-dimensional heat transfer by conduction at x. You have one-dimensional heat transfer by conduction at x plus dx. This one is because dx. And you have also convection. You have the convection heat transfer. And by first law, whatever comes, that system should leave the system, and therefore you will have Q dot Ct x should be equal to Q dot Ct x plus dx plus Q dot Cv. Okay. And if you solve this heat transfer and apply heat transfer equations, you will reach this equation here: d squared dt twice x squared hp ksc t minus t infinity is equal to 0. This is second order differential equation and the linear homogeneous, and it is easiest to solve. If you bring it in an easier form, you can say it is m squared, and this one is the theta, and therefore this differential part becomes d squared theta by dx squared. It is second order, and if you apply the parabolic equation to this one, you will get the roots and you find the equation itself. The result is a mx plus c2 e to the power of negative mx, c1, c2. You see, you have two constants. For finding these two constants, c1 and the c2, you need two conditions, two boundary conditions, because it is at the boundary. Okay, one boundary when x is 0, this is x coordinate, x is 0. Another boundary is this part, tip, when x is L. Okay, we have two boundary conditions, we should know them. First boundary is easy because at x is 0 we know the t base. T base is given. At the tip boundary condition, what happens at the tip? It is under question mark, because we should deal with the situation, with the condition which boundary is dominating at the tip. So there are main 4 boundary conditions. So these boundary conditions are 4 boundary conditions at the tip, the famous ones. The first one is that the theta at the theta means t minus t infinity. Theta tip is 0. When theta tip is 0, it means that t at the tip is t infinity. T infinity means, if I add another slide here, infinity means if this is the fin, this is surface or base that we have attached a fin to that surface. Here you have the base temperature, let's say that 100 degrees Celsius. This is the different color here. So here the temperature is T infinity, 25 degrees Celsius. I assume T infinity of the room. Okay. If it is 25 degrees Celsius, it means that this fin is too long, because the temperature is 100. Then temperature drops to 80. Then it drops to 60. Then it drops to 50. You see, it should be too long so that this temperature drop reaches 25 at the end of the tip, at the end of the fin. So therefore here L tends to infinity. This is mathematical condition, but some of the conditions have this L tends to infinity. Therefore L here tends to infinity. Another condition is that the theta tip is given, or T tip is given in the question. So the question gives the temperature at the tip. So the question says that, let's see that this one is 1 and the 2 and this is the fin. The question says that the temperature at the tip, this one, is 80 degrees Celsius. Okay. It is okay. You use the formulas here. We'll come to that formula. And the third condition is that the temperature doesn't change at the tip. So this one is given. See the third condition. Got one more slide here. So, let's say adiabatic tip. And most of the time, you have the adiabatic tip. Adiabatic tip means this is the fin. The area here, you see the area, it is very small area. If the area is very small, we will have heat transfer, because heat transfer is proportional to area. If this area goes down, then heat transfer goes down. Then it becomes as if insulated. So as if insulated. If it is insulated at the tip, then the temperature cannot change here. The temperature doesn't change here, and the d by dx is 0. Okay. This is the adiabatic tip. Let's go back to here. This adiabatic tip. And the one last is the convective tip. The fourth one is the convective tip. Convective tip means this is the fin. This is the most realistic one. Okay. So convective tip means here at the tip you have heat transfer by conduction. This one is conduction because this is material. We have Q dot CD. We take a small interface here. This one is the interface. Interface doesn't have any volume. Whatever comes should leave it. Therefore, you should have the convection here, because air blows over it. So you have the material. This one is the material, solid material, and this one is air that flows over it. Therefore, air takes the heat given off the tip. So here, Q dot CV is Q dot CD. And this one is the most real. Okay. Good. So this one is convective. So we have 4 different conditions. And the 4 different conditions, you can see that here we have the temperature distribution along the fin. It is given as theta by theta base, or T minus T infinity divided by T base minus T infinity. So this is the temperature distribution along the fin. Why it is important? Because we should know how the temperature changes and if this fin is useful or not. Okay. Say that I have a fin here. Here I have a hot temperature. I don't know the temperature here. So this is the T. Let's use a function here. We add another function here. Is T at the x coordinate, which is x. Okay. This one is T, and this one is x, and this one is the fin. This one is fin, and this one is base. So if it is x, most of the time it is exponential. Why? Because as you have seen this differential equation, it is exponential solution. For uniform fins we have exponential, but non-uniform fins it can be different. Okay. And then you will have some temperature here, which is T base, and that temperature drops in an exponential manner. You reach some temperature here. Okay. If you increase that length to infinity, if L goes to infinity, then this temperature goes to uniform temperature T is at 20 infinity. Okay. Good. This one is for L tends to infinity, T tends to T infinity. T infinity can be 0, 29, 10, whatever value is the environment temperature. This is the temperature distribution function. It is function. This part is function. Okay, this is also function. This is also function. This is also function. And the last part is the heat transfer rate from the fin. What is the value of heat transfer rate? This is not function, this is a value. You will find some value, for example, M. And it's this one. You will find some value, quotient L, theta base, theta tip. You have different values, tang, shine, etc. Okay, here you have the value. This is not a function. Okay. And you should know that these are all for uniform areas. Uniform. This is very important because you cannot solve this differential equation if it is non-uniform. I mean this differential equation. Because you will see that the area should be outside of the differential equation. Solve it. Now comes another thing here is that we can use the table or you can use the figure. This one is the easy, figure is easy. Table is difficult. Why it is difficult? Because it gives the formula and that formula is sometimes not good. Let's see the book. You go back to the book, the chapter 3. You have the fin efficiency. You see the table value. Here you have the efficiency. You can use this efficiency and find the heat transfer rate. You see have the Bessel function here. You have the Bessel functions everywhere. The Bessel and this one is also Bessel. Or you can use, these are the easy formulas. But anyway, the table is not easy. But the chart is easiest one because you are calculating the coordinate here. You have the coordinate, you are calculating coordinate and find the efficiency by intersection point. This is the figure one and this is another figure. This is for annular fins and this is for uniform and non-uniform straight fins. Good. And now we have the corrected length. Why do we use the corrected length? Because this one is mathematical advantage. You can say it. Mathematical advantage. Why it is mathematical advantage? Because convective tip is difficult. Convective tip equation is difficult. Okay. And we can convert it into the adiabatic tip by adding this distance, AC tip, the tip cross-sectional area, by the perimeter of the tip. The perimeter of the tip. Okay. You add it and you will get some amount of extra length, and this amount of extra length brings the tip to adiabatic condition. But it is not unrealistic, but it is realistic. It is realistic solution. Okay. Because since the tip has very small thickness. Okay. Therefore, we are using the corrected length to bring, this one is the convective tip, CV tip. Now this one becomes adiabatic tip. Okay, good. This is the problem that I have solved in another video. And now comes the efficiency of the fin. The fin efficiency is calculated by actual heat transfer rate from the fin to the ideal heat transfer rate from the fin. What do we mean by ideal fin? Ideal fin means that this ideal one, this one means that K tends to infinity. Okay, if the K tends to infinity, for example, we can use, this material is not possible to use infinite value for the K, but you can use higher values for the K. You compare the actual with the K infinity, or resistance. Resistance CD tends to 0. So if that is the case, then you will have the fin here, and you will have the flow of heat, Q dot CD. You will have the flow of heat, Q dot CD, and there is no resistance against it. This resistance is 0. If there is no resistance, then it means that whatever information you have as 100 degrees Celsius, that information propagates along the domain till the end at 100 degrees Celsius, because you have infinite, the infinite speed of disturbance, because the K is infinite. Therefore, the information propagates at an infinite speed. You have 100, you have 100, you have 80, you have 80. And then we are comparing the actual one with ideal one. If it is ideal, everywhere temperature is 100. If everywhere temperature is 100, the Q conduction is best. If the conduction heat transfer is best, whatever left is to remove by air. To remove by air. How do you remove by air? Then you will use Q dot CV. Q dot CV is H, area of the fin, into T base minus T infinity. Because there is no conduction equation here, K is infinity. Okay, conduction is perfect. There is only one thing left for convection. Okay, convection heat transfer, it should happen along the fin. We are using the fin area. And we should add that most of the time when we say fin area, we say the area top, and we say area bottom. Okay, and we say area right, and we have the area left. And here you have the area tip. Fin area means fin area. This area top plus area bottom plus area right plus area left plus area of the tip. But most of the time, this area tip is 0. Why it is 0? Because very small. Yeah, therefore you can neglect it. Good. If you divide these to that one, you will get the efficiency, and from efficiency you can find actual heat transfer rate. We can do fin effectiveness. This one has been proposed by 1999 Higgs. Higgs says that fin efficiency doesn't give us information about the performance of the fins. Why? Think that you have an infinitely long fin, L tends to infinity. Then this base temperature, 100 degrees Celsius, will drop to 20 degrees Celsius of the environment temperature, because it has an infinite length, and therefore the temperature drops. But the problem is that this infinite long fin has higher weight. So higher weight, if it has higher weight, it is not good option because it is heavy. Another bad thing about this one is cost. Okay, you have added cost, you have added weight. Therefore, Higgs proposes another efficiency performance meter, which is epsilon. That says that epsilon for one fin, this is for one fin. You see, there is one fin. This actual heat transfer rate with the fin. So this one is Q dot fin divided by no fin. So this area. So it will be, this area only uses convective heat transfer. Therefore, area of the base. So this shaded area, shaded. Okay, into delta T. And the Q dot fin you select from the chart. Here we have the table. So you select any of the values from the table or the chart or figure to calculate the efficiency. I can do one calculation, one simple calculation for one fin. Let's say that the simplest one is, so infinitely long fin. Okay, let's see what does it bring us. So if the fin is infinitely long, we will have the heat transfer as m, which is square root of hp kac theta base. Let's use it. Theta will be square root of hp kac. AC is this cross-sectional area, and in the theta base. This is epsilon. Rate with the fin. Here you have, and divided by heat transfer rate without the fin. If there is no any fin, then the heat transfer rate will be equal to H, area of the base shaded area. So you should see that. And in the theta base, again the same temperature difference. So from here you can cancel out the theta base, and here you see area C and the area B are the same. Area C is same as the area base shaded. Okay, so therefore you can cancel them out too. So you will have 1 by square root of H AC, 1 by square root of H AC, and so you will have 1 by H, which is the ratio of this H. You will have the AC, because AC and the AB are the same, and you will have perimeter square root of that one, and you will have the K. And let's write it in a neat way. You will have P into K into H into A. So let's see what does effectiveness bring us as an information. Let's play with the values. So it says that if you increase the K value, you have higher effectiveness. It is clear, because if you increase K, you will have better heat transfer due to conductive material, and you have good K, good heat transfer. But it says it is inversely proportional to H. Why? It says that if you increase H, epsilon drops. Why it drops? Because why do we need fins? We need fins to increase surface area, AS delta T, HAS delta T. This is the reason that we need fins. Because H value of the gas is very low. So H of gas is low, very low. If it is very low, then it means that air doesn't want heat transfer to accept, let's say, accept heat transfer. If it doesn't want to accept heat transfer, we should force it. How do we force it? We force it by fans, or we force it by increasing surface area of the fins. Therefore, we use fins where H is very low. We use fins where the gases are present. If it is liquid, most of the time we don't need to increase the surface area, because the liquids have higher H, and therefore the lower value of H, the better effectiveness of the fins. Okay, so we are forcing the heat transfer by using the fins. Good. So another last thing here is that the perimeter by area. So perimeter by area. So the perimeter by AC. Now let's see one example. Say that I have a rectangular surface. This is a rectangular surface. It has a surface, a cross-sectional area of 2 by 1. So AC is 2 into 1. It makes 2. Everywhere it is 2, and it is, no, it should be opposite. It is 1, it is 2, it is 1, it is 2. Okay, and the perimeter makes 4, and the 2 is 6 millimeters, let's say, millimeters squared. So what I can make is this. I have the same area, so it is, let's say, for 2 it makes 4, 0.5. Okay, it's again 0.5, again 4 here. So you can see the cross-sectional area is same, so it is 2 millimeters square, but the perimeter is 8, and half of it makes 9 millimeters. You can see perimeter increased, but the area is constant, therefore epsilon increased. What we have done is that we decrease the thickness, so thickness dropped, but the width, this one has increased. Okay, so this is the one method to increase the epsilon. Okay, so these are used to increase the effectiveness of the fins, and this is proposed by Higgs. And this one is for one fin. If you use the lots of array of fins, we call it array of fins. Here it is, array of fins. You can use the overall effectiveness. Overall effectiveness will be actual total heat transfer rate with fin. So we have how many fins? 1, 2, 3 fins. We add it, and you have also unfinned parts. We will talk about this one. And heat transfer without the fin. Without the fin again means if there was no fin. Okay. So firstly, unfinned area. Unfinned area is these areas. You see these areas? There are no any fins. Okay, these are area unfinned. This is also area unfinned. This is also area unfinned. This is also area unfinned. So you have heat transfer from area unfinned parts. So Q dot unfinned will be equal to H area unfinned into delta T, or T base minus T infinity. This is the definition of delta T. Area no fin. Area no fin is if there was no anything. If there was no fin. If there was no anything, then you would have the area as the width of this part, which is W, and then H of this one, let's say H. So it will be area no fin H into W. Okay, and then Q dot no fin will be equal to H into W, again the H, again T base minus T infinity. Now comes the fin area. You will have the fin area as, so let's say that area top plus area bottom plus area left plus area right plus area of the tip. So this one is area tip, this one is area top, this one is area bottom, and this one is area left, and this one is area right. So you add up them and you will have the fin area, and then Q dot fin will be from the, or using table, using chart. Okay, if you use table, it is best to use for uniform area. If you use chart, it is for non-uniform. Okay, because chart makes non-uniform area easier, and the table makes uniform areas easier. Okay, and here you can add that. Okay, here you can say that this tip area most of the time is small. Okay, therefore you can ignore it, but the rest is there. The area of the fin and etc. So this is the end of the lecture, and we have 2 examples that will be attached as a separate file. If you have questions, you can leave as a comment. Best wishes.